Somewhere in a darkened laboratory, a single particle of light is about to do something that should be impossible. It is going to make a decision and then wait. It will travel, it will land, it will be recorded by an instrument, and its journey will appear to be over. And then, a fraction of a second later, a scientist will make a choice, not about the future, about what that particle already did, and the particle will obey. For nearly a century, the strangest results in all of physics have come from one deceptively simple piece of apparatus, a wall with two narrow slits cut into it, and a source of light on the far side. From this humble setup, an entire scientific revolution was born. But in 1999, a team of physicists pushed it to its breaking point, and what they found seemed to violate the one rule we thought no experiment could ever break, that the past comes before the future. The experiment is called the delayed choice quantum eraser, and on its surface it tells a story that sounds like madness, that a choice made now can reach backwards through time and rewrite a history that has already happened, that a photon can somehow know what an observer will decide and behave accordingly before the decision is even made. Tonight we will walk through this experiment step by step and let it terrify us, and then only then we will take it apart and discover that the truth is not time travel. The truth is stranger. The real lesson hiding inside it is that space and time and the orderly march of cause and effect may not be fundamental features of reality at all. They may be something the universe assembles after the fact. To understand what breaks, we first have to understand what should happen. Let's send light through those two slits, but let's do it one photon at a time. A single, indivisible particle of light fired like a tiny bullet towards the wall. It passes through, strikes a screen behind, and leaves a single dot. One photon, one dot. We fire another dot. We do this thousands of times, and we wait for the pattern to emerge. If light were simply made of bullets, we'd expect two bright stripes behind the two slits, the shadow of the wall, printed in light. But that is not what appears. Instead, the dots arrange themselves into a series of bright and dark bands, a striped fingerprint of alternating light and shadow. This is an interference pattern. It is the unmistakable signature of a wave, like ripples from two stones meeting on a pond, reinforcing here, cancelling there. And here is the first impossibility. We send the photons one at a time. Each photon was alone. There was nothing for it to interfere with, except somehow itself. The only way to make sense of this is to accept something profound. Before it is measured, the photon does not travel as a single point along a single path. It travels as a wave of pure possibility. A smear of probability that passes through both slits at once overlaps with itself on the far side and only becomes a single definite dot at the instant it strikes the screen. The photon, in a very real sense, takes every pass at the same time. This is wave-particle duality's the beating heart of quantum mechanics. But now we become curious. We want to catch the photon in the act, so we place a tiny detector beside each slit, a watcher whose only job is to record which slit the photon actually passed through. We run the experiment again, and the very moment we are able to tell which path each photon took, the bands vanish. The interference pattern dies and collapses into two dull ordinary stripes, exactly what you'd expect from bullets. The wave is gone. This is the rule physicists call complementarity, and it is absolute. You can know which path a photon took, or you can see the interference pattern. You can never have both, the instant which way information exists anywhere in the universe, even if no human ever reads it. The wave behavior is forbidden. It is as though the photon refuses to be caught being in two places at once. Knowledge has a cost, and the cost is the wave. Remember this trap, because the entire experiment that follows is built to spring it and then impossibly to escape it. To spring the trap, we need a way to know which slit the photon took, without looking at the photon that lands on our screen. And quantum mechanics hands us a tool of breathtaking elegance. Just behind the two slits we place a special crystal made of beta-barium borate. When a single photon strikes this crystal, something remarkable happens. It splits in two new photons, each with half the energy, born at the same instant from the same point. We call them twins. One we name the signal photon, the other the idler. These twins are not merely similar. They are entangled, bound into a single shared quantum state, no matter how far apart they travel. measure a property of one, and in that same instant the other's matching property is fixed, whether it sits on the next table or the far side of a galaxy. Einstein hated this. He called it spooky action at a distance. But entanglement is real. It has been tested to exquisite precision, and crucially it carries no signal, no message, nothing that travels faster than light. It is correlation without communication. Hold on to that phrase. It will save us at the end. Now watch what this gives us. The signal photon flies up toward our screen, where it will help build a pattern. But its twin, the idler, flies off in another direction entirely, and because they were born together at the very same slit, the idler secretly carries the which-way information. The idler is a receipt, a record of the path the signal photon took. So if we catch that idler and read the receipt, then which-way information exists and complementarity demands that the signal photons show no interference. Two dull stripes, the trap is sprung. But here is the move that gives the experiment its name. What if, instead of reading the receipt, we destroy it? What if we send the idler through an arrangement of mirrors and half-silvered beam splitters that scramble the two paths so completely it becomes impossible, even in principle, to know which slit the pair came from? We have erased the which-way information, and when we do, the interference pattern returns. The photon, it seems, forgives us, destroys the evidence of its path, and its wave nature comes flooding back. And now comes the question that turns a clever trick into a genuine nightmare. What if we wait? What if the signal photon has already hit the screen, already been recorded, already finished its journey, before we decide whether to read the receipt or burn it? This question was first asked not in a laboratory, but in the mind of one of the great physicists of the 20th century, John Archibald Wheeler. Wheeler was the man who coined the term black hole. He was a living bridge between Einstein and the founders of quantum theory, and he had a gift for taking an idea and pushing it until it screamed. In the late 1970s, he proposed a thought experiment he called delayed choice. The premise was simple and devastating. Make the decision late. Wait until the photon is already committed, until it has, by every classical measure, already chosen to behave as a wave or a particle, and only then decide which question to ask of it. And Wheeler did not think small, to show just how absurd the stakes could become. He scales the experiment up to the size of the cosmos. Imagine a quasar, a brilliant beacon at the edge of the visible universe, its light setting out toward Earth billions of years ago, long before our planet existed. Now imagine that, on its journey that light passes a massive galaxy. The galaxy's gravity bends space-time itself, acting as a colossal lens, and the light can curve around it on either side to the left or to the right, to reach us. That light has been traveling for billions of years. The choice of which path to take around the galaxy was made before the Earth itself had even formed, and tonight an astronomer on this small planet points a telescope at that ancient light and decides how to observe it. She can set up her instrument to measure which side of the galaxy each photon passed and find particles. Or she can combine the two paths on her detector and find an interference pattern, proof the light traveled both ways at once. Her choice, made tonight, appears to determine what that photon did billions of years before she was born. Wheeler called this a strange inversion of the normal order of time, and he understood exactly how dangerous it sounded. But he was careful, far more careful than the breathless headlines that would follow. Wheeler did not believe we were sending messages into the past. His conclusion was subtler and in its way more unsettling. No phenomenon, he wrote, is a real phenomenon until it is an observed phenomenon. The past, he argued, has no fixed, finished existence except as it is recorded in the present. The photon never had a single definite history quietly waiting to be discovered. It had no history at all until we asked. For 20 years it remained a thought experiment, and then in 1999 a team of physicists built one. The experiment was carried out by Yoon Ho Kim and his colleagues, alongside the physicist Marlon Scully, and it remains one of the most beautiful pieces of optical engineering ever assembled on a single table. Let us build it together, one piece at a time. We start with a laser, fired at our familiar double slit. But just behind each slit sits a barium borate crystal, so every photon that passes through becomes a pair of entangled twins. And it matters which slit they were born at. a pair from the upper slit or a pair from the lower. From each pair, the signal photon travels upward through a lens to a detector we'll call D0. D0 rides on a motor sliding back and forth across the focal plane, counting where the signal photons land position by position. D0 is our screen. If interference is happening, this is where the stripes would appear. But the idler, the twin carrying the which way receipt, is sent in the opposite direction downward into a maze, and its path is deliberately longer. By the time the idler is finally detected, roughly 8 billionths of a second have passed since its signal twin already struck D0. Let Z settle the signal photon's fate is sealed first, already landed, already counted before its twin has even reached the choice that is supposed to decide its nature. Follow the idler in. First it meets a beam splitter, a half-silvered mirror offering a clean 50-50 gamble. Down one road lies revelation. An idler from the upper slit is steered toward a detector we'll call D3, one from the lower slit toward D4. And here is the key. A click at D3 could only have come from the upper slit, a click at D4 only from the lower. So if the idler lands at D3 or D4, the which way information survives and those signal partners must behave as particles. Down the other road lies forgetting. The idler is sent toward the final beam splitter, where the upper and lower paths are brought together and mixed beyond any hope of separation. Behind it wait two more detectors, D1 and D2. A click at either could have come from either slit, with no way, even in principle, to tell which. The receipt is shredded, the which way information is erased, and complementarity now demands that those signal partners behave as waves. So the experiment runs millions of pairs. Then the physicist sorts the data, not by hand but by correlation, matching each signal photon at D0 to the detector where its idler twin finally landed. 4 piles. The signal photons whose twins ended at D3 or D4 show no interference, a single smooth hump. Particles. But the signal photons whose twins ended at D1 or D2 assemble themselves into a perfect interference pattern. Crisp, bright and dark bands. Waves. These are the same photons, drawn from the same beam, born as the same crystals, recorded as the same detector, D0. The only difference between a wave photon and a particle photon is the fate of a twin. It will never see again, a fate that was sealed 8 nanoseconds after it was already dead. Sort the data one way, and the past was a wave. Sort it the other, and the past was a particle. The choice to erase the information or keep it was made after the signal photons had already written their history into the detector. And yet that history seems to bend perfectly to match a decision made in its future. So how do we escape? The answer hides in one quiet fact the headlines always omit. Go back to D0, and this time do not sort the data at all. Look at every signal photon together, exactly as it arrived. And what you see is nothing, no bands, a smooth, featureless blur. The total pattern at D0 never changes, not when we erase, not when we keep, no matter what we do to the idlers downstream. There is no moment at which the screen flickers from stripes to a blob. By itself, D0 shows no interference, ever. The interference was never something you could see at D0. It emerges only when you bring in the idler data from the future and use it to sort the signal photons into subgroups, a method called coincidence counting. And here is a secret that dissolves the paradox. The pattern tied to D1 and the pattern tied to D2 are mirror images perfectly out of step. Add them back together and they cancel, leaving exactly the smooth blur we already saw. The interference was always there, hidden inside the correlations, waiting to be revealed by sorting. We did not create it with our choice. We merely chose which already existing correlation to look at. Nothing traveled backward. No message reached the past. There is no retrocausality here, no time machine. And yet, do not let the relief fool you into thinking the strangeness is gone. It has only moved. Because the lesson that survives is this. The photon never possessed a single, definite history quietly waiting to be uncovered. Wave or particle, this slit or that slit, these were never properties the photon carried alone, through time. They are statements about the whole entangled pair, about correlations that span the gap between two twins and between two moments. Quantum mechanics simply does not store the world the way our intuition insists it must, as separate objects, each with its own private story, marching forward through an absolute time. So zoom out past the detectors, past the laser and the crystal, until our entire planet is a single pale blue point, suspended in the vast dark lattice of space-time. We tend to believe space and time are the fixed stage on which everything happens, but experiments like this one whisper a heresy that a growing number of physicists now take seriously, that space and time are not the foundation at all, that they emerge, woven after the fact, from a deeper web of quantum correlation that knows nothing of before and after, here and there. The future did not change the past. Something far more profound is true. At the deepest level, the past and the future may not be as separate or as real as they feel. We are not trapped inside the machine of time. We may be watching time assemble itself, correlation by correlation, from something underneath. If that thought thrills you as much as it unsettles us, stay with us, subscribe, and follow us deeper into the strange and beautiful machinery of reality.